Hello and welcome to another capacitor chemistry video. This one is a GCSE one and this one is all about bonding. I really need to get a logo. Okay, so this one is dedicated to my current year 10 class. Year 10, this is for you. I made one with you guys in class, but I thought let me just record one from scratch. So first thing we've got a piece of A4 paper over here. What I'm going to do is I'm going to split it into three parts because there's three types of bonding that you learn about in GCSE chemistry. So let me just draw a line there. And the first type of bonding, shout it at your screens. What are we going to start with? Right, I'll tell you what we're going to start with. We'll start with this one. Right, ionic bonding. At this point, I'd like you to pause the video and take 3 minutes, and only 3 minutes, to write down everything you know about ionic bonding. I'm going to drop in a disclaimer. This video will not have anything about dot and cross diagrams. No dot and cross diagrams in this video. Right, ionic bonding. You've had enough time. Ionic bonding. What do we know? We know we have metals bonded to non-metals. You also know that there is the transfer of electrons, and what happens to the electrons? The metals will lose electrons, and I'm writing that as an E minus. The non-metals will gain electrons, and that means they will turn into ions. Once a metal loses electrons, it will have a positive charge, and that plus VE means positive, and when non-metals gain electrons, they will have a negative charge. And then what makes them stick together? This is the mark scheme answer part. You have got strong electrostatic forces of attraction. And what's that between? Between oppositely charged ions. Right, now move the page up. When they stick together, what do they turn into? What do they look like? They look like this. So I'll draw a picture. You know what I'm drawing, right? Put some pluses and some minuses, so there's your ions. And that is a picture of a giant ionic lattice. Now in a lattice, these ions are not free to move. Why? They're stuck together because strong electrostatic force of attraction between oppositely charged ions. Okay. So these things, as a solid, they have a really high melting point, high MP melting point, and they've also got a high boiling point as well. And they cannot conduct electricity as a solid. They can, however, conduct when they're molten, which means liquid, or when they're aqueous, and the reason is the ions are free to move. So here we go, let's add that in as well. Can conduct when molten, that's a word for liquid, or aqueous. Ions are mobile. Wicked. Right, ionic bonding done. Right, next one. Let's zoom out on the page. Let's zoom out. Oh, nearly dropped it. Right, next one. draw another line, split the page again, and in the middle this time we're going to write covalent. Right, pause the video again, take 3 minutes, and come back. Covalent bonding. In this one, your teacher's probably going to get you drawing loads and loads of dot and cross diagrams, and they are really important for practice. This one we're not doing any dot and cross diagrams, but let's talk about covalent bonding. Covalent bonding, what have we got? We've got non-metal plus non-metal. What do? They both share electrons, and most of the time these ones cannot conduct electricity. Why? They have no free electrons, and these things aren't ions. They don't have ions either. So I'm writing no free electrons or no ions. Right, but covalent, it's not as simple as that. Oh wait, I just said simple covalent. Right, let's split it up. Covalent bonding, 2 types. We've got simple and we got giant, or macromolecular. Right, so giant covalent, there's 2 main ones I'm going to talk about, and one I'm going to talk about really quickly. So we got diamond, also known as girl's best friend. Diamond is really hard. Why is it hard? It's made out of carbon. But what these carbons got, they've all got 4 bonds. And we call it a tetrahedral structure. Now I've actually got a diamond with me. Hold on, I'm just going to zoom out a little bit. Take a look, this is my diamond. And every single carbon is bonded to 4 other carbons. It's a madness. Right, let's draw a picture of it. So the picture you're going to see in textbooks, the picture you'll have to draw if they ask you to draw a picture of diamond, something like this, where you can see your central carbon is bonded to 4 other carbons, and then they might ask you to extend it, and then you just draw more carbons joined on, but maximum 4 carbons attached, 4 bonds from each carbon. Now carbon in diamond is an allotrope. That means it's a form of carbon. It cannot conduct electricity because there are no free electrons. Electricity cannot conduct electricity. Right, the next giant covalent structure you need to know about is called graphite. Right, graphite is described as soft and slippery. Why? When I said this in class, year 10 were just shouting out layers, and yeah, there are layers that slide over each other. In graphite, there are 3 bonds from each carbon. And let me show you graphite. I got graphite here. Here's some graphite in a pencil. You probably got some as well. And if you want an actual model of graphite, we'll zoom out again. Whoa. Right, look at that. That is graphite. There are these purple things, and that just shows the layers. And from the top, it looks like hexagons. So the hexagonal rings, this carbon is bonded to 1, 2, 3, and there are layers, and in these layers we've got 3 electrons. So carbon can form 4 bonds. In graphite, it has 3 bonds and 1 free electron. It can conduct and a picture. We draw a hexagon, and then dotted lines, and those dotted lines represent that they're in layers, and there are 3 electrons in between the layers. So because of those electrons, graphite can conduct. The last giant covalent molecule you need to know is silicon dioxide. Silicon dioxide is sand. It cannot conduct electricity either. Right, now onto simple molecular. Lots of you probably shouting at your screen, hey, we've heard about diamond, we've heard about graphite, but what about the other allotrope of carbon? Allotrope means version. The other allotrope of carbon is called Buckminster fullerene. I've got it here. Look at that, that's Buckminster fullerene, or a buckyball. It's properly like a ball. That is simple covalent. It is not giant covalent. So, Buckminster fullerene C60. Other examples: CO2, H2O, CH4, that's methane, N2, that's nitrogen. These are all simple covalent structures. They've all got really low melting and boiling points. Why? Because they've got weak intermolecular forces between the molecules, and this is where you've got to be careful. Graphite, between the layers, weak IMFs between layers, but the covalent bonds are super strong. Right, now on to the last one. Last one is, yep, you got it, metallic bonding. Take 2 minutes, write down everything you know, and then come back. Okay, metallic bonding. If you guys said it in words, you would say there are positive ions with delocalized electrons. You're probably shouting delocalized electrons. Now I like to draw it as a picture. I think pictures are great. So if we draw it as a picture, there's some circles to represent the metal ions. Probably too many. They're all positively charged because metals lose electrons. And each one of these positive ions has donated electrons to the cloud or the sea of delocalized electrons. Now, they have properties that you'll know about. The properties are they can conduct electricity. Why can they conduct electricity? They can conduct electricity and heat energy. They can conduct electricity and heat energy. Why? Because they've got delocalized electrons that are free to move throughout the structure. And this is something that I've seen in mark schemes more and more nowadays, throughout the structure. So not just delocalized electrons that are free to move, but delocalized electrons that are free to move around the structure. They have also got high melting points and boiling points. And then I'm also going to tell you about alloys. Now metals, they're really malleable. Why are they malleable? Because they're in a regular pattern, but when you hammer them, you can mess up the layers, and when you move them, they could be reshaped. So metals are malleable, metals are ductile. Ductile means they can be drawn out into wires. Alloys are slightly different. So down here, I'll draw you an alloy. So here you see we have all of these metal ions. Let's draw the electrons in as well. But then we've got these two things here in the middle, and they would be atoms of different substances. So an easy alloy to name is steel. Steel is an alloy of iron and carbon. An alloy is a mixture of a metal plus at least one other substance, and these have different properties to the original metal. Yeah? Right, I think I'm going to leave it at that. I forgot to show you one thing. My lattice. My ionic lattice. So there's my ionic lattice. Here's my actual ionic lattice. Take a look. Beautiful, isn't it? Here we got positive and negative ions. They're all stuck together. It's really, really hard to pull them apart. Why? Strong electrostatic force of attraction between oppositely charged ions. I've said in covalent bonding, we got simple and giant covalent bonding. One thing to point out here is from this whole sheet of bonding, we've only said intermolecular forces here and here. We only talk about intermolecular forces when we're talking about simple covalent and we're talking about graphite. That's it. There's no other place on this whole entire sheet on bonding where we've mentioned intermolecular forces at all. With ionic, electrostatic force of attraction. With metallic, we talk about delocalized electrons, but nowhere else do we talk about intermolecular forces, just simple covalent and graphite. Alright, thanks for watching. If you've got any questions, please stick them in the comments. See you next time.